Hello class. In the last video lecture we discussed about operational amplifier as a comparator, especially as a zero level detector. In this short video we will discuss about how operational amplifiers can be used as a comparator in order to compare two different voltage levels which is other than zero. So let's recap our last class of non-inverting and inverting comparators. So let's consider this circuit where the input signal V1 is applied to a non-inverting terminal, whereas the inverting terminal is grounded. So that means a 0 volts is going to be appear at the inverting terminal, and the non-inverting terminal will give the actual sinusoidal signal, which is a signal keep changing. So this circuit was developed using a multi-sim. So when you consider the very first positive half cycle, if I am explaining this one using with the two different half cycles, positive and negative, on the very first positive half cycle, the input signal is V positive because it is applied to a V plus, or the non-inverting terminal is greater than the V negative because obviously the V negative is going to be 0 volts. So as the input signal rises, so it's going from 0, 0.1, 0.2, 0.3 and so on, all those values are greater than 0. So the V input is greater than 0 for the very first positive cycle. So that's only in the positive cycle of a sine wave. In the first positive cycle, V input is going to be greater than 0. So the output voltage, which is going to be shown in the square wave. So remember, when the V positive is greater than V negative, the output voltage, the output shoots towards the maximum saturated, or V output maximum, or VCC. So in this example, it's considered as a 15 volts. So the output voltage will be around 14.5, will be close to 15 volts, but it's not going to be equals to 15 volts. So this whole first positive half cycle, the output voltage is going to be always 14.5. When the input signal goes negative, which is going to be below 0, so then definitely V positive is going to be less than V negative, because V negative is going to be always 0 because it is grounded, and the V positive, that is where you apply an input signal, but the input signal is taking a negative value in the negative cycle. So the negative values it's going to be considering, and the negative value is always less than 0. So the output will shoots back to a maximum negative level, which is going to be negative VCC. So this is where the negative VCC is, and approximately you are looking at negative 14.5 volts or close to negative 15 volts, but it's not going to be equal to negative 15. So as we consider, the input signal is a sine wave, the output signal is a square wave. So OpAmp as a zero level detector can be used in the conversion of a sine wave to a square wave. When you can observe, there is no phase shift between the input signal and an output signal. So this means this is a non-inverting comparator. So when you look at another circuit where the input signal is connected to an inverting terminal and the non-inverting terminal in this case is grounded. So when I observe the same positive and negative half cycle of a sinusoidal signal, so during the first positive half cycle, V negative is greater than V positive because V positive is held at 0 volts, and the V negative, meaning that the negative terminal is getting the positive cycle. So positive voltage is greater than 0. So that means V negative is greater than V positive. The output shoots towards a maximum negative level. Again, it is going to be approximately negative 14.5 volts. and during the negative cycle, so V negative less than V positive, meaning that V positive is always going to be 0 volts, but V negative is a negative potential, because our V negative is receiving a negative half cycle. So this half cycle is going to be received by a inverting terminal that is less than 0. So the output will shoot maximum, which is going to be plus 14.5 volts. So these are the two examples. If we compare here, in this case, this is a inverting comparator because the phase difference between the input and output signals is 180 degrees. So in the previous circuit, the phase difference is 0 degrees because the input signal and output signal will almost starting at the same point. Here in the next circuit, which is going to be an inverting comparator, where the input signal is going higher, at the same time the output signal is getting lower. So exactly opposite phase shift, which is going to be 180 degrees. As you remember, or as you recall, in an inverting amplifier, the output is always 180 degrees out of phase. If it's a non-inverting, the output is going to be in phase with the input signal. So these are the two circuits we talked about in the last lecture. And both circuits are comparing with the 0 volts, whether you connect the negative terminal to a 0 or positive terminal to a 0. And both circuits are referring to as zero level detectors. So how can we change this one? So other than comparing with 0, which is going to be greater than 0 or less than 0, how can we make sure we can build a comparator so that we can compare the input voltage with another voltage other than 0? So let's look at the non-zero level detection with voltage divider network. So this particular circuit is a non-zero level detector. Look at, because no terminal is grounded. The negative or the inverting terminal is coming from one of the voltage divider network, and the non-inverting terminal is actually getting a 10 volt peak sinusoidal signal. So in this graph shown here, the input signal or the signal in the blue color is a sine wave, that is the input signal, and the output signal is in the red. So this one is input signal, and this signal is actually applied to a positive terminal or a non-inverting terminal. The red one is the output signal. So no terminal is grounded, so this is not a zero level detector, and this is still a comparator because there is no feedback in the system. So let's look at, so that, okay, the input signal is 10 volts peak. Guess what the input signal is? The negative terminal is connected to this point A. So let's call this one as a point A. And this is a voltage divider network. When you can observe this, R1, R2 are in series, and of course both resistances are of an equal value, and it is getting the power from that 15 volt source. So look at here, so that 15 volts is going to be applied to an voltage divider network with an equal values of resistances. So that means the voltage at this particular point will be divided exactly into half, because we have only two resistances, that's why it's half, and it's an equal values of resistances. That's why this resistor R1 is going to carry 7.5 volts drop, and R2 is going to be carry another 7.5 volts drop. So the voltage at the point A is going to be 7.5 volts. So that is a constant voltage because this 15 volts is a DC supply. So the input signal here is comparing with 7.5 volts. So let's take a closer look on the input and output signals. Okay. So this is my input signal, which is going to be a sinusoidal waveform. And the peak of the signal is going to be 10 volts. And the negative peak obviously the negative peak is going to be negative 10 volts. So that's the positive peak and this is the negative peak. So the reference voltage, the input signal is now comparing with 7.5 and that's a positive voltage because this 15 volts is coming as a positive 15 volts. So the reference I'm going to call as V reference. So on the y-axis it is going to be located at 7.5 volts and that's a positive. So this line is the reference voltage. So right now the reference is not 0 because it's not grounded. The reference is 7.5 volts. So let's recap again how a comparator is going to work. So if the V positive is greater than V negative, then the output is going to be VCC. If V positive is less than V negative, then the output is negative VCC. So the V negative is always 7.5 in this particular example. So V negative is always 7.5 volts. It's not changing, but the V positive is changing because it is a sine wave. So the signal below the 7.5, let's look at 0 point. So no voltage exists, the output is going to be 0 for an ideal op-amp. As the input signal is increasing, the concept is it should cross the reference, otherwise the output signal will not be change its states. So from this point to this point, the input signal is below the reference. So the input signal is applied to a positive terminal. So from this particular point to this point, the input signal is below the reference. So that means V positive is less than the V negative. So from this point to this point, input signal is greater than the reference. So input signal is applied to the V positive is greater than the reference, which is 7.5 volts. And for the whole rest of the negative cycle, so starting from that point to for the whole cycle, again the input voltage is less than the reference. So the input voltage is applied to V positive, which is less than the reference. So if the input voltage is less than, then it's going to give you a negative VCC. So if you look at the output signal here, I'm getting the maximum negative signal and it is going to be constant voltage. If the V positive is greater than V negative, which is the output rises to a positive VCC. After that, V positive is less than the V negative, the output will get a negative VCC. So that is a non-zero level detection. It's based upon the same concept. The voltage at the inverting terminal is greater than the non-inverting terminal, then it is going to be negative VCC, otherwise it is going to be a positive VCC. So if you reverse the inputs as we saw before at the zero level detector, if I change my inputs, it's still 15 volts, that's a positive voltage. So 7.5 volts is connected to the V positive because that's where it is coming off of from a voltage divider network. And the input signal is applied to a inverting terminal. So remember, if an input signal is applied to an inverting terminal, the input signal and the output signal are going to be out of phase by 180 degrees, and you can clearly observe as the input signal rises, the output signal drops. So here the blue one is going to be the input signal and the red one is going to be the output signal. But in this case, the reference is still a positive 7.5. So let's draw that I/O characteristics again in much more in detail. Let's say that's a sinusoidal signal, that is an input voltage. Now the reference again is 7.5 volt, that is a positive 7.5. Just keep in mind that because the voltage divider is getting the supply from positive 15 also, the reference voltage is going to be positive 15. The peak of the signal is 10 volts and the reference is still positive 7.5 volts. So that's the peak of the signal and this is the reference voltage. So the reference voltage will meet the positive half cycle in 2 points. Those are the 2 points the output of the op-amp will switch its polarities. So let's draw the output signal, how it is going to be look like. Remember, the input signal is applied to a negative terminal. V positive is always going to be 7.5 volts. So V positive, again coming to the facts of an op-amp, V positive greater than V negative, it is going to be VCC. The V positive is less than V negative, it is going to be negative VCC. Initially both signals, or initially the reference is 0. Initially the reference is at 7.5. The input signal is at 0. So input signal is at 0, meaning that V negative is at 0, but the V positive is at 7.5. So V positive is greater than V negative initially. So the output signal rises to M positive VCC. So it will keep stays on the positive until up to that point. So at that particular point, the input signal is greater than the reference. So this part of the signal where the input signal is greater than the reference, because input signal is applied to a negative terminal, V negative is greater than the reference. Reference is the V positive. So V negative will be greater than the V positive. So the output signal will shift to a negative potential and to that region. So right below that reference, so right now after that point, the rest of the signal, that whole signal falls below the reference. So the reference is greater. So in this particular case, V positive is greater than the V negative. So V positive is greater than V negative. So if the V positive is greater than V negative, the output will shoot to a positive until that whole rest of the signal. So that is a non-zero level detection with a voltage divider network. So we can change the values of resistances to compare this input signal with any other voltage other than 7.5 volts. Depending upon what values of resistances, the output voltage or the reference voltage is going to be changed. So let us consider an example on how to solve these type of problems in order to draw a signal. So let's look at here. The input signal is applied to a non-inverting terminal. So V positive is input signal. Keep in mind that if it is a sine wave, it is going to keep vary from 0 to it's a maximum peak to 0, 0 to negative peak to back to 0. So that input signal is a sine wave which is applied to a V positive terminal. And again, the peak of the signal is 5 volts. And on the negative axis, the negative peak is -5. So we know that one, so that's what the V positive is. And V negative is connected to this point in the voltage divider network. So our next step is finding out the voltage across that particular point, and which is going to be the reference voltage in this case. So let's calculate the V reference. So as you already aware of, the voltage at that point is total voltage coming in, which is the 10 volts, because this voltage divider is getting the signal from the 10 volts. So the total voltage is 10 volts times V reference is with respect to the ground, which is at 5K, which is across the 5 kilo ohm resistance. So the 5K is going to be on the numerator. R1 and R2 are the 2 kilo ohms and the 5 kilo ohm resistances are in series. So the total resistance is addition of those two, which is going to be at 7K. So approximately the reference voltage is, when you calculate, that's 50/7. So approximately 7 volts. So make sure you did some calculation and you will get a value approximately 7 volts as a reference voltage. Let's do one thing. Let's change back our input signal to 10 volts peak, because the reference voltage is a little bit higher. So it's better to change the reference voltage or the input signal approximately 10 volts. So I'm going to just do a quick change here. So the input signal is not 5 volts. I'm going to consider it as a 10 volts. But the reference voltage will not change because it is still coming from a VCC. So it's a total source voltage VCC multiplied by the voltage across the 5K. So 5 kilo ohm resistance is going to be on the numerator, divided by the total resistance, which is going to be 7K. So it's going to be 50/7. So it's approximately 7.1 volts. So I'm going to consider the reference as 7 volts. And again, remember, this is a positive voltage. So the reference is going to be positive 7 volts. So that is where the reference is. So let's draw the output signal, how it is going to look like. Keep in mind that input signal is applied to a non-inverting terminal, meaning that the input signal and the output signal, there is no phase shift or there is no phase difference between input and output signals. So let's look at very first thing I want you to, once you find out the reference voltages, identify which portion in the signal the reference voltage will cut through. So there are two positions where the reference voltage will cross the actual input signal. I'm going to call this one as a point A and this point as a point B. So starting from point 0 or the origin, the signal from 0 to A, so this is the signal from 0 to A that falls below the reference. So in this case, reference voltage is greater than the input. Reference is applied to a V negative. Input is applied to a V positive. So meaning that V negative is greater than V positive. If the V negative is greater than V positive, up to that particular amount of time. So up to that point A, the output is going to be a negative value. After the point A, so in between point A to B, so this one is from 0 to A. So now let's look at from A to B. So from A to B, input signal is greater than the reference. And keep in mind that input signal is applied to a V positive is greater than V negative. So if V positive is greater than V negative, the output will shoot up towards its maximum voltage level and it will stay constant until that point B occurs. And from point B to rest of the whole full cycle, or until the signal crosses back at point C. So from point B to C, the whole signal will get a negative value. It is going to be same as in between from 0 to A, because the reference voltage is greater than the input voltage. So it is going to be gives you a negative voltage. And this signal is going to be continuous because the input signal is a sinusoidal wave. So you can change the voltage divider to get a negative reference voltage. So instead of having a positive reference voltage, so far we talk about, we can use a negative reference voltage by simply changing the supply to a negative 15 volts. So right now this voltage divider is getting negative 7.5 volts. So the input signal is applied to a positive terminal. Keep in mind that if the input signal is applied to a positive or non-inverting terminal, there is no phase shift with respect to an input and the output signal. That's why you can observe there is no phase shift in this particular graph. But if the signal is applied to an inverting terminal, there is always going to be a phase shift. Look at here, if the input signal is rising, the output signal is drop. So there is a 180 degrees out of phase between those two signals. The only difference is you are comparing with a negative 7.5 volts in both cases. Instead of having only a positive reference, you are comparing with a negative reference.